Hi friends, in this video we are going to discuss about speed control methods of DC motor. Let's see. Generally we know that EB back EMF is equals to V minus IARA. Of course, before that we know that EB is directly proportional to phi into N, nothing but K phi N. So K phi N is equals to V minus IARA. So the speed N is equals to V minus IARA by K phi. So either by changing the armature resistance, we can change the speed. Either by changing the flux, we can change the speed. Either by changing the voltage also, we can change the speed. Hence, the speed control methods of one is the flux control method, and next one armature resistance control method, and next one voltage control method. These are the speed control methods of DC machine. Let's see each and every one. First, take the heading, the flux control method. Are you ready? Right? Let's go for flux control method. First, I am talking about shunt machine. The flux control method of speed control for shunt motor. In DC shunt motor, let's see how we can control the speed in flux control method. In this method, for example, this is my armature, is like this. Is it okay? And here we have a field winding. Of course, here we have a armature winding, and this is connected to a rheostat. An extra rheostat placed in series to the field winding of motor. And here actually first place this rheostat at what position? Minimum position or maximum position? Take this at minimum position. When this is minimum position, the current flowing is, for example, the field current IF. Generally, take this at minimum position and control the rotor speed up to 1000 RPM, for example, rated speed, whatever it may be, rated speed. Maintain the rotor speed at rated speed and place this rheostat at minimum position. Now slightly increase the rheostat position. When the rheostat values are increasing, then automatically the resistance of the field winding increasing. When the resistance of the field winding increasing, the field current will reduce. Nothing but flux will reduce. When the flux reduces, then automatically the speed of the machine will increase. Sir, how it is, sir? Generally, this is a DC shunt motor. That's why EB is equals to V minus IARA, where speed N is equals to V minus IARA upon K into phi. Here, by increasing the rheostat position from minimum to maximum, in that condition, actually the field current through the field winding is reduces, nothing but the flux reduces. When the flux reduces, then automatically the speed increases. Is it okay? Sir, for example, I want to reduce my speed. How, sir? My rheostat already at minimum position. Now tell me, how I can reduce my speed? To reduce my speed, I have to increase my flux. How? I have to increase my field current. How? I have to reduce my field current. How it is possible? By reducing already rheostat at minimum position. Then how we can reduce that? So generally this flux reduced is okay, but flux increased is not possible with this flux control method of speed control. Hence, this is only for above rated speeds. Above rated speed control method is our flux control method. You should remember this point carefully. Is it okay? This is a above rated speed control method. This is not applicable for below rated speed control method. Is the first most important thing. And next one here, in this method, the flux reduced. When the flux reduces, then speed increases. Very good answer. And what about torque? Torque directly proportional to phi into Ia. When the flux reduces, then automatically torque also reduces. So in flux control method, one, the speed is increases, but the torque reduces. Are you getting or not? Are you getting my point? So what happens, sir? For example, this is the speed and this is the torque. For example, this is the rated speed. What is our position now? Above rated speed only. We are increasing the speed of the motor from rated speed to the above rated speed, not for below rated speed, sir. So we are increasing above rated speed. When the speed is increasing at this condition, what happened to torque? The torque is reducing. Are you getting or not? Here the torque reducing. But what is the relation between torque and speed? We know that the power P is equals to omega T or simply NT. Here the speed is increasing but torque is reducing. As usually, when the speed increases, then the torque reduces. Then what about the power? The power is constant. In this condition, the power is exactly constant, even though speed increases or decreases. But here, see, what is the relation between torque and speed? Torque T is inversely proportional to speed. When the speed increases, then the torque reduces, inversely proportional, nothing but this is a rectangular hyperbola. So in flux control method, the motor acts as a, how it is acts as a, the motor acts as a constant power, variable torque drive. Variable torque, we know that variable torque drive, this is very important for us. So in flux control method, the motor acts as a, in flux control method, the motor acts as a constant power variable torque drive. This is very important. And here the relation between torque and speed is inversely proportional to each other in above rated speed range. Alright, sir. This is generally the flux control method of DC shunt motor. Okay. This is only applicable for above rated speeds. I given you clarity. How much percentage of speed we can increase in this method? Yeah, exactly. In this method, we can increase the speed from 1 is to 2 range, nothing but from 1000 rpm to 2000 rpm for normal machines. If you are using interpoles, then you can improve the speed 1 is to 4, 1000 to 4000 rpm. So 1 is to 4 range when we are using interpoles. If you are using interpoles, it is easy to improve the speed from 1 is to 4 range. Sir, why this is in normal case? Because if the flux is reducing below certain level, then what happens are armature reaction effect increases. Yes or no? When the main field flux reduces, then the armature reaction effect increases, which is very dangerous. That's why don't reduce the flux below the certain limit. Are you okay? Yes or no? So this is simply the flux control method of DC shunt motor. Is it clear? In this method, we are going to discuss about the flux control method in DC series motor. Right? Let's see here. Very simple. But in series motor, the flux control methods are nearly 2 to 3 types. Let's see, we are going to discuss each and every one. The first method is field diverting method. Field diverting will be done in this method. Let's see how we can divert to the field. For example, this is my field winding which is connected to the armature of the DC motor. Actually, it is like this. Is it okay? Here what the current is called ISE. Here what the current is armature current. Here now I want to control the flux in this field winding, but it should not affect the armature current. How it is possible, sir? If you take a resistance here, it will affect the armature current also. That's why for that purpose I am taking a extra resistance is called diverting resistance. By changing the diverting resistance, we can make it easy. So let's see here. What I am doing is that here an extra resistance is connected which is in parallel to the field winding. Then actual current is divided into two parts and the current flowing in this winding is called diverting current and remaining current flows in this one. Now in this current, actually here the total current appears, but in this flowing the current is called ISE. This ISE is equals to total current minus diverting current. By changing the resistance, we can change this ISE by changing the diverting current. How we can increase or decrease this ISE? In generally, first take the RD at minimum position and set the rotor speed at rated value. Then after, since gradually by increasing the rotor resistance, by increasing the diverting current, by increasing the rotor resistance or by increasing the diverting current, nothing but we have to change this rotor. What is the diverting resistance? We have to increase the diverting current and simply we have to reduce the series current, series field current. When the series field current reduces, then the main field flux reduces. If the main field flux reduces, then automatically speed reduces. Is it okay? No, sir. Because the speed is inversely proportional to flux. That's why when the flux reduces, then the speed increases and the torque reduces, but power is equals to nt. The power is constant. I said you already. This is simply the flux control method, which is the field diverting method. Here also, the machine acts as a constant power variable torque drive only. Of course, this is the general thing up to now. We can use like this. The flux control method in series motor is field diverting method. Are you clear? Now, the second one is tapping method. Here, we are going to make a tappings for field winding without changing the armature current. Let's see how, for example, this is my field winding which is connected to the armature. For example, this is my armature winding, and here, for example, tapping 1, tapping 2, tapping 3 and tapping 4, like this. We have a many number of tapping as per our requirements. For example, if it is connected to tapping 1, the flux is phi 1 and the flux is phi 2 and the flux is phi 3 and the flux is phi 4. In generally, for tapping 1, more number of turns included. That's why the phi 1 is greater than, phi 2 is greater than, phi 3 is greater than phi 4. But we know that speed is inversely proportional to flux. That's why the speed n1 is less than, n2 is less than, n3 is less than, n4. Like this, we can reduce the speed like this. Here also we can increase the speed. Here also we can increase the speed, because when it is connected to here, for example, 1000 rpm. Now I connected here 2000 rpm. I connected here 3000 rpm. I connected here 4000 rpm. Like that, we can increase the speed. But for example, if you want to 2560 rpm, it is not possible. I'm sorry, sir. If you want 2000, okay. If you want 3000, okay. But don't say in between 2 and 3000. If you want 4000, okay. But don't say 3750. I'm sorry. So this is a stepwise speed control. But here we can make it a smooth speed control by changing the variable resistance, diverting resistance. So this is simply the second method, which is called tapping method. And what is the third method? The third method is that series and parallel connection of field winding. We can make it easy. So let's see the series and parallel connection of field winding, how we can control the speed in that method. Let's see, that is very important compared to these two. Compared to these two, that method is important because some formulas are there, and compared to series motor, shunt motor is important for competitive examination. Okay, whatever, let's see here. A third one is series parallel of field winding. Let's check it. For example, the total field winding is divided into two parts. Those two field winding parts are connected in series like this. This is my field winding, which is divided into two parts and connected here. And in next time, the same two parts connected in parallel. So this is, for example, my armature, and the field windings are connected in parallel like this, like this. This is series paralleling of field winding. See here, n by 2 number of turns, Here also n by 2 number of turns and the current is I. Here the current is I, nothing but here the current is I by 2 and here the current is I by 2. Here n by 2 number of turns, here also n by 2 number of turns, like this. In generally, I said that the speed is inversely proportional to flux, nothing but the speed is inversely proportional to MMF, which is nothing the number of turns into current, because we don't know the flux how much it is, but we can make it easy to calculate MMF, ampere turns, right? Yes or no? Are you okay? So listen here, what is the MMF for series connection? The MMF of series connection is equals to n by 2 of I plus n by 2 of I. Ni by 2, Ni by 2. How much, sir? Ni. This is the MMF for series connection. What is the MMF for parallel connection? MMF for parallel connection is equals to n by 2 and I by 2 plus n by 2 and I by 2. Nothing but Ni by 4 plus Ni by 4. Ni by 4 plus Ni by 4 is equals to Ni by 2. This is for parallel connection. These are the, we have two MMFs. Let's calculate at which condition the flux is constant. Let's see. What? Here, the speed in parallel connection to the speed in series connection is equals to n is inversely proportional to MMF. That's why MMF in series connection to the MMF in parallel connection, nothing but what is the MMF in series connection? It's very simple, Ni upon what is for parallel connection, Ni out of 2, Ni gets cancelled, that is equals to 2. So the speed in parallel connection is equals to 2 times of the speed in series connection. Are you getting or not? Here we have a 2 parts, that's why this is 2. If you have a 3 parts, that is 3 times, 4 parts 4 times, 5 parts 5 times. So the speed in parallel connection is equals to n times of the speed in series connection. Of course, here the change is the flux, hence torque also changes. What is the relation between speed and the torque? When the power is constant, the torque is inversely proportional to speed, yes or no? So the torque in parallel connection is equals to 1 by n of the torque in series connection because of inversely proportional. This is for constant power drive. If you maintain constant torque, for example, if the torque is constant, then this is completely changed. The speed in parallel connection is equals to root n times of the speed in series connection, and the power in parallel connection is equals to, what is that? What is the relation between power and the speed? The speed and the powers are directly proportional. So power in series connection. Are you okay? Right? So this is generally for speed and the power and speed and the torque. In our DC series motor, the speed control methods. What are the 3 speed control methods? What is that? One is the field diverting method, second one is the tapping method, and the third one is the series paralleling of field winding. This is important for us. Right? Thank you.